Everyone. This is Avinash Abhyankar from the New York Genome Center. And first of all, I want to thank the organizers for giving me this opportunity to interact with you all. It has always been a pleasure. And today I'll talk about genomic medicine and AI. So, before I delve into the AI part of the talk, I want to walk you through a typical diagnostic odyssey story. So, this story is based on the cases that I have worked on over the years, and obviously the names have been changed. But after listening to the story, you should get a typical idea about what patients suffering with genetic disorders typically go through. Uh, so this is the case of Maya, who is 10-year-old. First time she stumbles during a soccer practice, and the parents brush it off as clumsiness, which is kind of typical. The stumbles then become falls. The falls morph into tremors, and this brings them to their first doctor visit. The first visit yields shrugs and basic blood tests, leading them down a winding path of consultations. And each of these consultations leads to a dead end. And the months they turn into years, and after all of the MRIs and ECGs and muscle biopsies and negative results, the hopes they start fading away. However, uh, hope emerges in the form of Dr. Kumar. Again, as I said, the names have been changed. Uh, Dr. Kumar is a geneticist known for her pioneering work in this field, and she studies Maya's medical history with an meticulous eye and introduces them to the latest advances in genomic medicine. And she orders a genome sequencing test. Uh, Weeks later, the results arrive, and a previously undetected rare genetic mutation is identified and is linked to a neuromuscular disorder. So finally, they at least have a mutation that is linked to the phenotype. And the path forward wasn't easy, but at least knowing that there is a mutation which is rare and it is associated with the symptoms that Maya was facing, they at least had hopes of some kind of a treatment. It took another 6 months to identify the appropriate course of treatment. Maya's odyssey was long, arduous, but it did not end without any result. She ultimately got a diagnosis and treatment. So, diagnostic odyssey is a reality, even in developed nations like the United States. And not everyone is as lucky as Maya. And there are a few reasons why people with genetic conditions have to go through so many like weeks, months of testing and misdiagnosis. So there are some significant challenges. The first is knowledge gaps. Many primary care doctors they lack in-depth knowledge of the genetic disorders, which can lead to missed clues during early consultations. Then there is scarcity of specialists, especially geneticists and genetic counselors. And depending on where you live, your insurance, and specific condition you're dealing with, it might be like really hard to find the specialists. Additionally, the intricate nature of genetic testing demands highly trained professionals and sophisticated labs, which creates a significant barrier uh, for access to diagnostics. And lastly, like there are a whole bunch of diagnostic tests for genetic disorders, and they range from chromosomal microarrays to genome sequencing, and selecting the appropriate test is also essential in reaching a accurate diagnosis in short amount of time. So these are all like the different challenges. So, uh, like, how can we overcome these challenges? And here comes like the AI part of the talk. And before we go into like how AI can help in overcoming these challenges, I want to just go through a few relevant concepts here. So we are all on the same page. Uh, so we all always hear a lot about like AI and machine learning and computer vision. All of them, they are like interrelated, but no, they are slightly like different concepts. Artificial intelligence or AI is a broad field encompassing any technique that enables machines to mimic human intelligence. This includes tasks like speech recognition, decision making, and problem solving. Machine learning is a subset of AI that focuses on training computers to learn and improve from data without being explicitly programmed. Computer vision is all about training computers to understand and interpret visual information like images and videos. It powers features like facial recognition on our phone or self-driving cars navigating on the streets. Natural language processing or NLP. So this field focuses on enabling computers to understand and process human language. This includes tasks like machine translation, sentiment analysis, chatbots that can hold conversations. And lastly, a lot of us have uh, been introduced to ChatGPT, for example, or Google Bard recently in the last half a year to a year. And these are examples of large learning models or LLMs, which are a type of uh, natural language processing models, but they are trained on massive amounts of data, like billions of words, for example. This allows them to generate human quality text, translate languages, write different kinds of creative content, and answer questions in an informative way. And these fields are constantly evolving and intersecting. The lines between them can blur, and new applications are emerging all the time. So, this is not like an exhaustive list of the concepts related to machine learning and artificial intelligence. No, I'm only noted down the ones that are relevant to like what I'm going to like talk about today and how we at the New York Genome Center we are using these the methods for genetic diagnosis. So, like going back to the challenges that we enumerated a few slides ago, now how can we solve these using AI? So, the first thing that we could do is come up with clinical decision support systems at the primary care level. This would help in triaging and initial assessment at the primary care facilities. Considering that not all the clinicians at the primary care facilities are uh, like well experienced in genetic disorders, AI-powered systems can analyze the patient data, including electronic health records, family history, symptoms, and flag potential genetic risks based on the complex algorithms and vast medical databases. So this can alert the healthcare professionals to consider genetic factors they might otherwise overlook, prompting further investigation or referrals to specialists. And these AI-powered platforms can provide high quality and accessible education resources about specific genetic conditions, filling the knowledge gap until a specialist contact is possible. The second aspect that can be worked on using AI are virtual consultations and remote support. And as we discussed earlier, I mean, getting hold of specialist geneticists or genetic counselors is really hard, even in developed nations. Like having the ability of virtual consultations and remote support is going to be very helpful, uh, uh, especially for countries like India, where we have scarcity of genetic counselors or clinical geneticists. So AI facilitated telegenetics platforms can connect patients with specialists in the remote locations, overcoming geographical barriers and increasing access to expert advice. These AI assistants can also assist during consultations, like help the remote clinician like get a summary of the patient information and just highlight the relevant findings and suggesting the next steps, which is also a good use of the AI assistants. These assistants can also generate a differential diagnosis based on the patient data, prompting further investigation and discussion, and also offer up-to-date findings in the treatment and treatment recommendations tailored to specific condition being investigated. Yeah, and this is very important because the field of genetics is always evolving. New papers are published every week, every month, and new gene disease associations they come up very frequently. So it's very important to stay up to date and get the latest information about any gene disease association. Informed decision making, and this is something that is on the patient side. So understanding and acting upon genetic information can be very challenging for lay people just because of the complexity of the information. To help the patients understand all the intricacies of the genetic diseases or the tests they are being recommended, AI-powered data visualization can translate complex genetic data into clear and engaging visuals. NLP assistants can explain genetic findings in plain language, tailored to patients' level of understanding or even the patient's own language or dialect. And predictive modeling can also be used to estimate the likelihood of developing a disease based on different factors. So this is on the patient side. And lastly, uh, we need to bridge the gap, when it comes to advanced diagnostics. So, as I mentioned earlier, the tests that are available for diagnosing genetic disorders, they might be complex and require complex facilities and people of varied expertise. And again, you may not have access to these type of facilities everywhere. So, designing efficient and accurate diagnostic tests utilizing AI algorithms to analyze the data from high throughput genetic tests is essential. This will lead to lower costs and also wider accessibility. We can also decentralize the diagnostic networks using AI-powered algorithms. And again, this is going to help in improving access to remote populations. And while genetic testing has become like faster and cheaper, uh, the deciphering the complex results like those from exome or genome sequencing, they still remain a true hurdle. And uh, from data analysis and interpretation to variant classification, AI algorithms can help in each and every step. And in the next few slides, I'll show you some real world examples. So this is a paper that came out of our lab earlier this year in October, and now this paper describes how we are using rapid whole genome sequencing for critically ill infants with complex congenital heart disease. So we have been doing rapid whole genome sequencing for almost like 2 or 3 years now, or even more, and we have pioneered this process over these years and used a whole range of machine learning and AI algorithms to make this test really rapid in terms of turnaround time. To give you a perspective of what I mean by rapid, uh, the mapping of the first human genome took over a decade. So the Human Genome Project started in 1993, and the first draft was released in 2003. Uh, Now, fast forward to 2023, a typical genome sequencing test delivers results in about 4 to 6 weeks. Rapid whole genome sequencing, on the other hand, is pushing the boundaries even further, and we aim to complete the entire process within a mere couple of days. So, like going from a decade to 4 to 6 weeks, we now are targeting this full test being done in a couple of days. And uh, like this test is like highly complex, and it utilizes all of the DNA of a person's genome. Uh, and like I said, we are targeting a significantly shorter time frame as compared to traditional sequencing tests. And it provides a fast diagnosis for critically ill patients, particularly children, where a rapid diagnosis can be crucial for guiding treatment and improving outcomes. So the typical indications for rapid genome sequencing are critically ill children with undiagnosed conditions, patients with suspected rare genetic diseases, neonates in neonatal ICU with congenital anomalies, cancer patients with complex tumor profiles. So all these like indications, they require us to like come up with an answer as quickly as possible. So how do we try and figure out like cutting down this time? So the human genome is 3 billion base pairs, and sequencing the genome of one individual generates in excess of 90 billion data points, which is huge. So for each patient, we generate that amount of data. And the major steps in the genome sequence analysis, they are like primary, secondary, and tertiary analysis. So the primary and secondary analysis is mostly related to bioinformatics and pre-processing of the actual raw sequencing data and making it available for tertiary analysis. So while like machine learning and AI algorithms are used in primary and secondary analysis, I'm not going to go into like details of that in the interest of time. But I will like describe a little bit in detail about the tertiary analysis, where we connect the genetic signatures with the patient's phenotype. And tertiary analysis is where a lot of human hours currently go in, and this is where AI makes the biggest difference. So, what is tertiary genome data analysis? This is the final and crucial step of interpretation, now where the vast amount of generated data is transformed into meaningful insights. The tertiary analysis dives deeper, adding biological context and interpreting the identified genomic variants to understand their significance for research or clinical diagnosis. And it relies heavily on specialized bioinformatics tools, clinical databases, genomic knowledge bases, and it requires expertise in genetics, statistics, and sometimes like specific disease areas. So, how do we go from several days spent on tertiary analysis to hours using AI? So, here is how we approach it. We use a mix of AI technologies, including machine learning, computer vision, natural language processing, large learning models, all of them specifically trained on medical literature and databases. So first, we start right from the clinical notes. So what we do is we transform the clinical notes, whether they are like handwritten or they are like in electronic format. We either use like computer vision or natural language processing to convert the clinical notes into structured keywords. These are like called as human phenotype ontology terms or HPO terms. And once we have transformed these clinical notes into a structured format, it's easier for us to programmatically process them later on during the process. Then the next step is to find the needle in the haystack. A typical genome sequencing yields about 2 million to 4 million mutations in any given individual. So we need a way to go down from these millions of variants to a shorter list that can be like then analyzed further in relation to that particular disease. So here we use specially trained machine learning algorithms to filter the variants and bring it down to a manageable list of few hundred. And now, like within these few hundred variants that we end up with, we again use like advanced neural network trained algorithms. And these algorithms, they are trained on known disease causing mutations. So the model it already has a profile of how a disease-causing mutation looks like. So based on like these models, like we further narrowed down the list of mutations into a really handful list of mutations. And lastly, we use like large learning models, again trained on medical literature and databases to draft a report. And this report is then ready for review by a human. So this is how like we are using the machine learning and other algorithms to in each and every step of the tertiary analysis. And this allows us to go from like several days of work to finishing the same thing in a couple of hours. So, like, what's next? Uh, so, thanks to all the advances in related technologies, including AI, something that used to take a career can now be achieved in a matter of months. For example, crystal structures. If you look at a few decades ago, like deciphering the crystal structure of proteins, it used to take like a whole career for someone. And now, using machine learning and artificial intelligence algorithms, the few years ago, Google published a whole catalog of 20 plus thousand protein structures just based on machine learning algorithms. While this is different from actual like deciphering the crystal structure in the lab, uh, having a blueprint of the uh, tertiary structures within months is a big advance. Similarly, like whole genome sequencing, it used to take years, and now it's being completed within days. And uh, again, like in the research field, there are like meta-analysis of thousands of scientific papers. Like for example, if someone wants to like summarize all the work that has been done for a particular disease, say for example, type 2 diabetes, someone would like spend like a half a year to a year to like read all the papers related to type 2 diabetes, and they would summarize like everything into one big paper. Now, recently, it has been shown that using machine learning algorithms and artificial intelligence, you could do the same thing in hours. So, like, we have made a lot of advances, and we have all these tools at our disposal. So, how do we use them, and how do we navigate this AI revolution in healthcare? And this is where like I want to like also mention that even though these tools are showing promise, we have to use them with caution. The uh, data is like a double-edged sword. uh, so all the AI algorithms and other algorithms that I mentioned, they are being trained by humans, and they are being trained by using some data sets, right? So whatever data you provide it to the algorithm, it gets trained on that. So there is also like bias sometimes in how the data is being trained. And uh, another fear that we always have is the black box mystery. Not all the machine learning algorithms. So, like for say, for example, like ChatGPT or Google's Bard. I mean, the original idea for ChatGPT or OpenAI was to have all the code open source, so everyone knows exactly how a decision is being made by that particular AI algorithm. But because of the complexity of like training these models, all the money that goes into training these models, uh, having a open source system is not financially viable. So more and more, all these large learning models and these proprietary algorithms, they are getting like sandboxed, closed. So we don't know like how the decisions are being made, and especially when we start to use these type of algorithms on patients, it becomes even difficult if we don't know how the decisions are being made. Then we have a regulatory maze. The rapid evolution of AI has outspaced the existing regulations, so we need clear guidelines to ensure ethical development, use, and accountability in healthcare. And again, there comes a question of responsibility. So when an AI-powered tool makes a mistake, who bears the responsibility? So we need to make legal frameworks to address the liability and protect the patients. And lastly, and this is the most important aspect, which should we should never forget, at least for now, is that AI should not be considered as a replacement to human judgment. It should be used as a complement, and clinicians need proper training and support to understand the intricacies of these AI algorithms, and they need to be trained properly to work effectively with the AI tools and make informed decisions for their patients. So, all the developments that have happened recently and over the past few years in the AI, they are definitely going to change the way we do healthcare, and it's going to benefit both the clinicians and the patients. But at the same time, we should use them with caution. So thank you, and I hope I was able to provide you some new information regarding how AI algorithms are being used currently in the field of genomic medicine. And I wish I was able to take any questions, but feel free to reach out to me. The organizers have my contact email. So if anyone has any questions, feel free to reply to me. Thank you.